Hi everyone. In this lecture, we're going to be looking at the notion of trying to solve integer programs by successively generating valid inequalities that allows us to iteratively get closer and closer to the convex hull of the original feasible region. So that idea it's central in modern mixed integer programming technology nowadays. So it's really important to have a grasp on how it works and how it can be combined with the branch and bound method that we see in last class. So today we're going to focus exclusively on the notion of generating these inequalities, how we can generate and even devise a method that can solve optimization mixed integer programming problems using those. But then later on, in the end of the course, we'll see how we can actually combine the two things and how they are actually combined in developing a mixed integer programming solver. All right, so let's first start with this notion of valid inequalities, what they are and what make them valid. So just to get the context right, we are once again trying to solve these integer programming problems where a feasible set is the intersection of a polyhedral set, which has formulation like so, and Z, remember here, means the set of integer numbers. So X is the intersection between or even all the integer numbers within this polyhedral set. Okay. And from what we've been seeing in the last lectures is that we know that the convex hull of X is a polyhedron or a polyhedral set. And we know that there is a finite set of inequalities, now represented with this tildes, A and tilde B, such that they represent explicitly the convex hull of X. So basically, this is telling us the following. If you are in this sort of space where you have your integer points like so, these being X, there is a finite set of inequalities, perhaps say this one, and then this one, then this one, that one, that, and that one, that, for example. And that would devise the convex hull of these integer points. So there is always a finite number of inequalities that you can use to represent that. So in principle, that kind of motivates the idea of trying to search for those, because we know that once we have the convex hull of X available, we can solve the integer programming problem by actually employing LP solving, which we are very good, we are very efficient, and so on and so forth. Okay, so if we knew that collection of inequalities that generate the convex hull, that's all we needed to solve the problem, right? But of course, if that was that easy, we wouldn't be, having that many classes on different methods and how to devise a method for solving IPs. So we are not gonna be typically have full knowledge of those, but what we can do is devise a method that iteratively try to approximate that collection of inequalities that form the convex hull by successively adding constraints to AX less or equal than B. So basically the idea is that once we look at the linear relaxation, so this would be our set P, and somehow by having this formulation, infer that we can remove parts of this set that are not representative for the original convex hull or are not part of the original convex hull. So basically what we're trying to do is to do this exercise of thinking of this of some sort of a piece of wood that you're trying to, or you can think about this as a diamond to be lapidated. So you're trying to obtain this you know, this is your diamond right there. And what you're trying to do is to little by little, you know, add cuts to this to somehow get rid of this excess part that is in there. And this cut, and it actually called the cut because, you know, you're trying really to cut off this part perhaps, or this part, is by this derived by the notion, or by the means of what we call a valid inequality. And these valid inequalities, they were going to be designed in a way that you can use them to cut the part of P that doesn't belong to the convex hull. So P minus convex hull of X in this picture would be this area in orange here. That's what you want to get rid of. All right, so this is, let me put it here, that this is P set minus convex hull of X, right? And the way you show is that we say that the inequality, so we're going to be using these pi and pi 0 to be coefficients for it. We say that inequality is valid if it does not cut off any of the original feasible points of the set X. So you can generate valid inequalities. So you can generate inequalities, but for them to be considered valid, they have to be such that this is observed. That is, when you add, so you can see that here orange is a valid inequality because actually it's a really good valid inequality because it's cutting all that excess that was here, but it's not really cutting any feasible point. So if you come up with something, say, that looks like so, or, you know, perhaps like so, this is not a valid inequality because it's cutting out this feasible solution. And it has to be such that the inequality is satisfied by all points in X. Okay, so a valid inequality cannot cut off points from the original feasible set. So one misconception sometimes is when you think about, for example, branch and bound. When you're doing branching, you're not generating valid inequalities in the branching process because, you know, remember what we did. Let me go back to this picture here. This is fine. So when we have this part of the feasible region, or even better, we set a cut. Let me think about when we found the optimal solution for the LP relaxation here, and that generated a cut saying we want things that are above here and things that are below here. And you can see that this is not a valid cut because it's cutting out these points. So, you know, the process of branching doesn't generate valid inequalities at all. It's just something that I've once heard someone saying. So the questions we're going to be trying to answer in this is, well, okay, this is a beautiful inequality, you know, really tight, cuts exactly what we want in this direction. But how do we obtain inequalities that are this useful? That's point number one. And point number two is, and how can we use that? I mean, okay, I generated this and it looks pretty good. So, but it still doesn't, you know, if I still solve this as an LP, my optimal solution is here, and that's not integer. So how do we use this in a systematic way? You'll probably be guessing by now, but it involves, you know, going about and generating a new one of these, and then carry on until you say find an integer solution. But we'll look into that as well. So before we present the Chvátal-Gomory procedure, we need to understand two underlying concepts. The first one is this notion of valid inequalities, but for LPs instead. So we just seen a condition for which a constraint is said to be a valid inequality. But we were discussing valid inequalities for X, the set of integer points. But before we get there, we need to think about valid inequalities for P, which is the linear relaxation for it. And likewise, an inequality would be valid for P if it doesn't remove any of the feasible points from P. But one way, in the case of P, there is absolutely no way we can test every single feasible point because this is a continuous feasible region. So what we can do is instead try to devise a set of conditions that we can, from the original inequalities, derive be assured that we're deriving a valid inequality for P. And to derive a valid inequality for P, the logic extends like so. So we have the feasibility set, which is given by this. And we're going to be generating inequalities by multiplying the rows, the constraints by non-negative weights and combining them. So we'll end up with something that looks like so. And the way for that, this condition is guaranteed. Perhaps I can even write it instead like so. Let me redo this. So what we do is something that looks like so, with no negative weights, and then combining the rows. And then what we're going to do next is then to make sure that whatever we do to generate these inequalities is such that they look like this. So we're kind of a safeguard guaranteeing that this condition is not broken. And this is exactly what is behind this condition here and here. Okay. And how can we derive these? Well, we can use a duality argument because whenever we talk about combining, doing non-negative or using non-negative weights to combine constraints, that's basically what you're doing whenever you think about linear duals, really. So thinking about a valid inequality of this form, in which we want this to be feasible for all P, for all X in offset P. So let's think about posing this as a problem where I'm trying to find the maximum I can put on this side without violating the feasibility condition. So we'll be maximizing this, making sure original feasibility conditions are satisfied. And now if you think about the linear dual of this, so you have this multiplier U associated with these constraints, all right? You can see that the linear dual looks like so. And you can see here, the combination of rows we were talking about. So just by looking at, the conditions associated with finding these multipliers, you can see that these multipliers will be such that, if you think about this pair, dual feasibility conditions are satisfied. So taking non-negative weights and combining the rows such that this is observed leads you to this dual feasibility condition, which is what is in there. So that's the first one. Now, to show this is just a duality argument. If you do go about and actually maximize this and find the maximum, then you can use a strong duality argument to pose the following. You know that these two things will match. And by definition, this is the case, so you get the inequality there. But even if you're not willing to optimize, you also use a weak duality argument. So you could use a weak duality argument saying that this is the case, and it will still hold because this will be less or equal than that, which is less or equal than that. So this is a way that we can use a primal dual pair to show that if you're thinking about combining constraints while retaining feasibility, these are the conditions we're going to have to observe. And weak duality gives us this condition that allows us then to write these two. Okay, and then if you actually go about and actually maximize this, you can even use strong duality if you want. So this is valid inequalities for linear programs, for LPs, okay, which is the first step we need. Now, if we think about IPs, the way to generate, surprisingly, the way to generate valid inequalities for IPs is it's a simple operation of rounding, really. So basically, let's think about one dimension. So this is the real line, and then we have 1, 2, and then we have this integer number, which is rounding down this value b. If you have a constraint saying that y, which is integer, is less or equal than b, the way to generate a valid inequality for IP is to move this to that point then. Because if this is the case, then this is a valid inequality where you're not removing anything for the set where the feasibility set is given by these blue points that are integer. And that's about it. And surprisingly enough, combining the previous result with this is all we need to generate a sort of a universal method for developing valid inequalities for IPs, for the set X. So let's just start with a numeric example. So consider my set X being this polyhedral set intersecting with the integers, and my polyhedral set is like so. Notice that we kind of given a highlight to the constraints. So we are the conditions that X is greater than or equal than 0 is kind of encoded there. So this is a notation novelty, I guess. So that being the case, let's apply what we just seen. So first, I'm going to generate a valid inequality for P. And the valid inequality for P means finding a collection of non-negative multipliers that I can use to combine my constraints. And what combine means again? Basically, I get this number and multiply both sides here, this number multiply both sides here, this number multiply both sides there, and then I add them all. So I'm doing a linear combination of my constraints. Okay, this has also an interesting interpretation in terms of cones that we're not gonna dwell into here, but you can think of doing iconic combinations of the constraints. But let's think about that another time. So basically, I think that the main challenge here is that you're thinking, where does that come from? And that's the main challenge behind generating valid inequalities. Really, how do you set up these U's to generate these valid inequalities? This is where actually the research is full going, because what we actually have is, instead of general methods that can generate these U's, is ad hoc methods, problem-based methods that can generate valid inequalities for the structure of that problem, say set covering problems or knapsack problems, and you can relate that method with those of finding these U's. But for having an arbitrary, a general way of generating the multipliers U's, it is the current challenge. It is the main challenge. But anyway, assuming that in this case we generated a set of multipliers, and by the way we defined LP valid inequalities for LPs and valid inequalities to then generate valid inequalities for IP, like we're doing now, any set of U would do, as long as they are non-negative, it would work. The problem is that it might be so that your valid inequality is not that great when you actually go about using it. But anyway, this is what we get. So multiply these both sides by 2/7, 2/7, and then multiply this by that, and then I add them, and I get this constraint here. Okay, and this is valid for P. Now, I know that looking at this thing here, I can use the notion of valid inequalities for P, and because X is integer, and this is less or equal than, I can round down these things, and this will still be valid, because I will just be making this pi prime X that is less or equal than pi X. Prime was not perhaps, let's, there you go, right? So this is still going like so, because, because I know I have information on the problem, the X is an integer, so you can round down this thing to make this integer, and this will still be valid inequality. But now comes the trick, is that I can also use the notion of rounding on the right hand side, and that leads me to something that is valid now for my original integer problem, because these are integer, and this is integer. So I'm recovering this. And I end up with this inequality 2x1 less or equal than 5. which it might, is most likely not valid for P anymore, but it's certainly valid for the set for this set. And the question is whether it's good or not, whether it's helpful or not. It's what we're going to look into next. But the fact is that you have a valid inequality. And this step-by-step procedure is exactly what is the Chvátal-Gomory procedure. So defining it a bit more formally, let's consider this set X, which is the intersection of them two once again. And then we have this matrix A, which is an m by n matrix with columns like so. And we have a collection of non-negative weights, one per each row of A, one per constraint. So you can see that if we follow this set of steps, this first step generates a valid inequality for P, because we just showed how it is the case. Sorry, there's a transpose missing here. That's one. Now, you can think about this as kind of the other way around. If you think of x's as your multipliers, and because the x's have this condition that they are non-negative, by rounding these down, you're still generating a valid inequality. And the argument is exactly that, is because you're certainly going below the original pi, right? But another way of thinking is you can think of these as the new use of this combination. And because they are positive, this is not going to violate the original constraint x equals b, lesser or equal than b. And finally, now what you can do is come on the right-hand side and make it integer. And that, because we know that that generates a valid inequality for x. So we generate a valid inequality for P, and we change it into a valid inequality for x, capital X. And that's the Chvátal-Gomory procedure. Perhaps the most striking result of them all, which is quite tricky to demonstrate, but it is a really powerful result, is that what is designed is shown here in theorem 4. Every valid inequality for x can be obtained by applying the Chvátal-Gomory procedure a finite number of times. This is because the procedure is somewhat simple. It's really hard to believe that, to convince yourself at least that this is true. We'll in an exercise we'll have the chance of looking into this for the binary case, because the proof is long but doable. But and you can find several references out there that can show this in a more general case. But this is basically telling us the following: in principle, every valid inequality is achievable. The challenge is by applying this procedure. And you can see that what is the actual challenge here is this thing. Oh, these two, right? Which is the same. Finding this is this challenge. And basically what kind of ends up happening is that, looking at the structure of the problem, you kind of figure out ways to devise ad hoc valid inequalities. And then basically the process kind of goes the other way around. If you can show that this valid inequality can be generated, if that inequality that you're trying to show is valid can be generated using a suitable Gomory procedure, Chvátal-Gomory procedure, then you can show that it is a valid inequality indeed. So it tends to use this in the other way around. Because coming out of the blue with these vectors U is, challenging if you're trying to really find good ones. Those that are actually doing the service of cutting out parts of the set B that don't, they're not fully enveloping the integer points. Right. So yeah, this is the Chvátal-Gomory procedure to generate valid inequalities. All right, we'll stop here. This video is a bit long now, and what we're gonna do next is looking at how we can use this to devise a method that can actually find solutions for integer programs. So see you in the next video. Bye bye.